What's up, guys? In case you are worried that I'm not bathing and changing my shirt, I'm just doing back-to-back videos here. So I'm good, taking care of myself. Hope you guys are doing the same and enjoying being locked into your homes. Anyway, so here we go. I think we're at April 15th, and we are a week and a half in, and we should, at this point, have a pretty good idea about what we're doing with limits. But in the spirit of excessiveness, we are going to continue to review this. So my hope is that you can look at the key and get all these right without even checking this video. But if you are checking this video for certain problems, feel free to speed up the playback. Feel free to fast forward to the problems you need, of course. But I'm just going to pull out my key. I'm not going to actually work them all. That's pretty slow in the interest of getting done more quickly. I'm just going to go through my answers. And I'm going to really, hopefully at this point, you're starting to see the way you can think a little bit more quickly with these problems. All right, so here we go. All right, so I'm actually going to skip over the fill in the blank worksheet for just a couple reasons. One, the key's up there. If you look at the key, I think you're fine. If not, definitely send me an email or a text and I'll explain why. And two, just because it's an open notes test, so probably won't be asking a ton of those questions this year in the year of the coronavirus. Anyway, just taking a look at this second part of your assignment, which was to review of the graphical, algebraic, and trig limits. I'm going all the way back to the beginning on some of these. So I'm going to start with some trig, talk about continuity a little bit, just a little bit of everything. So you can see here on number one, that was a rule because I got 0 over 0, and it's one of my trig function of trig of something x over something x. I can take 1 over 1 and get 1. This one, really simple, tangent of 0, 0. When you get an answer, you're great. This one, remember, we don't deal with cotangent, so I change it to a 1 over tangent, then do the limit. And because I got 1 over 0, I'm going to say D and E because the bottom is not squared. Okay? Now, this next one's a little tricky. And remember, the whole idea about being squared is that you're guaranteeing that it's positive. So number 4, I like giving these problems like this to you. It doesn't appear like it's a big deal at first. A lot of people actually miss this by putting 1 over 1, but remember, we don't deal with cotangent. But look what happens. If I move the cotangent down to the denominator, make it a tangent, I've got a 1 over x tangent x. Now, when I plug a 0 in there, I get 0 for both, so I get 1 over 0. So I know there's a VA. Well, why didn't I write D and E? Because the bottom's not squared. Well, here's the thing, though. If you think about the graph of these, the graph of x kind of looks like just y equals x, looks like that. The graph of tangent x kind of looks like that. So if you think about it, as I'm coming into the right side of 0, like 0 from the right, both of those are positive, and I get a plus times a plus, which is a plus. But if I come in from the left side of 0, both of those are negative. So it's like a negative times a negative, which is also a plus. Well, that means that the bottom, no matter what, remains positive. The top, so it's almost like it's squared, right? It's the reason why the squared makes a difference is because you're going negative times negative is positive. But this would be negative times negative from the left, which is plus, positive times positive from the right, which is plus. Either way, it's plus. Of course, the top's always going to be close to 1. So this VA right here, this VA must have been going up to infinity on both sides. So I'm going to go and say positive infinity. All right, number 5. People miss number 5 a lot because on number 5, they look at it and they go, oh, yeah, 4/5. But the difference is, look, if I plug a 0 in, 4 times 0, 0, tangent is 0, 0. But there's no 0 there. It's just 5. 0 over 5 is 0. Be careful about that. Although on number 6, because that is a rule, you did get 0 over 0, 3/2. Number 7, again, I don't deal with that. You don't have to, you can't deal with cotangent, so you move the cotangent up, plug a 0 in. 0 times 0 is 0. Here, 0 over 0, so 12/5. Here, it's not 0 over 0. It's 4 over 0. That's undefined. Bottom's not squared. It's not even weird like number 4. It's got to be going in different directions. It must be a D and E. All right. Looking at number 10, Number 10, I can't deal with these cosecants, so I'm going to take the 5x as part of the cosecant, as is the 2x. So that comes down, that goes up, and I redo the limit. That's a rule, and I get 0 over 0, 2/5. Here, can't deal with the secant, move it up, plug a 0 in, 0 times cosine of 0. So cosine of 0 is 1. So 0 times 1 is 0. Number 12, I do get 0 minus 0 over 0, which is 0 over 0. So I know there's a hole, but I have to deal with this. So I'm going to put that over that and that over that. And I didn't rewrite it, but if I put that over that, I get 0 over 0. That's a rule, 8 halves. And if I put that over that, I get 0 over 0. That's a rule, 4 halves. So 8 halves minus 4 halves is 2. All right, so a little review on those. And then let's jump down to a, hold on one second. Let's jump down to one of these piecewise functions we were dealing with earlier. So I have this piecewise function. It looks like y equals -5, y equals 2x plus 1, y equals 1, y equals that, y equals that. I have basically 5 lines. A couple of them, 3 of them are horizontal lines. A couple of them have slopes. I really don't want to graph it, but I can answer all these questions just understanding the idea of piecewise function limits. So the first 4 were just asking you for values. So f of -3, well, where's it equal? It's equal there. Plug in a -3 and I get -5. F of 0 is equal also in the second equation. And I get a 1. I'm sorry, f of 0 is a 1. F of +3 is not equal anywhere. It's just less than or greater than. So it doesn't exist. And f of 4 is equal there. And when x is equal to 4, the f of 4 was equal to 3. Now this asks about the limits, okay? So for the limits, so for number 16, that was a 3. Number 17, the limit as I approach -3, I'm going to have to check from both sides. So from the left, it's -5. From the right, it's also -5. Since they match, the limit's -5. At 0, from the left, it's 1. From the right, it's 1. Left and right are the same, must be 1. Doesn't matter that there's not a value. I didn't ask if it was continuous. Remember, limits don't care about values, all right? Even though the value did exist there. Limit at 3. From the left, it's 1. From the right, it's -1. Those don't match, so the limit does not exist. And then the limit as x approaches 4. From the left, it's -2. From the right, it's +3. Those don't match. And again, that limit would not exist. All right? Let's look at number 21. We've seen these problems before. Whenever you get a 0 over 0, what does that typically look like? Normally I say the word typically, but maybe I did on yours. This is an older key, but it usually looks like a hole. There is a chance, again, we've talked about this, where if you factored and canceled the limits out and you redid it and then you got a number over 0, then what originally looked like a hole would actually be a VA. But typically 0 over 0 means a hole. And of course, yes, I would factor, cancel, redo the limit. I would use my trig rules if necessary, because I have more options now. And then if I do learn derivatives, I could do L'Hopital's rule, but we don't know that yet. 22, what happens when you get a number over 0? Well, that's going to mean a vertical asymptote always. Does the limit exist there? Never. But sometimes I do write infinity or negative infinity, so often I will check from the left and the right to determine the value of the limit, or maybe whether it exists from either side. But the bottom line is limits do not exist at vertical asymptotes, even though occasionally I will write infinity or negative infinity. All right, looking at number 23. Number 23, limits to infinity. Remember, limits to infinity are all about growth. Okay, and according to this, if the power on the top is bigger, the highest power on the top is bigger than the bottom, it's growing faster on the top than the bottom, which means this fraction is approaching either infinity or negative infinity, but I have to check the sign. So really, I can kind of avoid looking at all this and think, what happens if I plug a negative number in there? I get a positive on the top, but a negative on the bottom. Plus over minus is minus. So I end up going to negative infinity. And again, if it's growing faster on the top, I know I'm going to either plus or minus. It's all about finding the sign. And then the hard way to do it would be to actually go in here and divide each of these by an x cubed. Now, if I do that, I end up getting like 2x here, and I end up getting -3 over x and 7 over x squared and 1 and -5 over x cubed. And then when I do the limit, all those fractions with x's on the bottom go to 0. And I end up with just an infinity over a 1, a negative infinity. Sorry, actually, I end up getting a negative infinity over a positive 1, which is negative infinity. But that's a hard way to do it. This is the easy way to do it. All right, when the values match, the growth rate is the same, right? So you use the coefficients, 5/2 right there. And then right here, when the power is bigger on the bottom, again, these are all limits to infinity. Don't go using these rules when the x goes to 7 or x goes to 4. Like, don't look down here at number 27 and go, oh, higher power on the top, it must be infinity. Guys, if you're going to a number, plug the number in and evaluate it that way. But here I'm going to infinity, higher power on the bottom must be 0. Right here, see how I snuck a 3 in there on you? Don't be looking at these powers and go, oh, 0. Right here, I'm going to 3, so plug a 3 in. 27 minus 6 is 21. 27 minus 6 plus 1 is 22. I'm done. All right, really pay attention to what you're doing. All right, we are now looking at 27 right here, going to 4. 16 times 3 is 48 minus 4. 4 minus 3 is 1. All right, now if I was going to 3, that would be a VA down there. Be totally different, but pay careful attention to what you're doing. See right here, same problem, but with a 3. If I plug a 3 in there, I get 27 minus 4 is 23. 3 minus 3 is 0. What does that mean? It means there's a VA, right? This is not my answer, but it does mean there's a VA. And since the bottom is not squared, it must be going in different directions. And that would mean that the limit does not exist. All right, looking at 29 and 30. 29, again, I'm plugging the 3 in, the top and the bottom, and I get negative 23 over 0. But so it tells me, I know that that's not an answer. I know that there's a VA here, right? And if there's a vertical asymptote and the bottom is squared, it must be going in the same direction. Now, which direction is that? Infinity or negative infinity at this VA? Well, the bottom is guaranteed to be really close to 0, but positive. The top is going to be really close to negative 23. Negative over positive is a negative, must be going to negative infinity. And it's so much easier than plugging in 2.9 and 3.1 and trying to figure all that out. Although you could. Number 30, if I plug a 2 in, I get 0 over 0. That means there's a hole. So I got to factor it, and I did. Cancel out the hole that caused that 0 over 0 to occur. And then all I have left is an x minus 1. Redo the limit in that. Here, I'm back to a trig limit. Don't make the mistake of saying 6/3. Remember, there's no x there. Always plug the 0 in first. Plug a 0 in, that becomes 0. Tangent is 0, 0 over 3. That is 0. Okay? Here, notice it's 6x and 3x, a little bit different, right? This gives me 0 over 0 when I try. So I can use my rule 6/3, which is 2. Number 33, people freak out on 33 all the time. Guys, cancel the x's. You plug in a 0, you get 0 over 0. Cancel the common factor, and I'm left with a limit of 4/3. Well, limit of a constant's the constant. And then right here, okay, this is a curveball thrown at you. The limit of sine of 4x as x goes to infinity. So basically, you have to think about the graph here. What is the graph? Now, we have rules on infinity for rational functions because rational functions have either horizontal asymptotes or they go up or they go down. But what's a sine curve do? It just oscillates. In fact, this one oscillates between -1 and 1. The period is changed from a regular sine of x, but that doesn't really matter. It's still going up and down to -1 because of the amplitude is 1 right there. Well, according to the definition of a limit is the y value that a function approaches. Well, this is not approaching a y value. This is oscillating between every one of the infinite y values between -1 and 1. It just continues to go through them all. It's actually more wrong to just say -1 and 1. Because what about -1/2? It actually goes through -1/2 a whole lot more than it goes through -1. Right? For every one time it does that, it hits -1/2 twice, or positive square root of 3 over 2 twice, or 0.9 twice. So anyway, definitely, if you see oscillating between two fixed y values, we say the limit does not exist because there is not a single y value that this is approaching. And then finally on 35, people miss this all the time too. They say 4/3, but wait a minute, I'm not going to 0. Don't forget to plug the number in. If I plug 15 degrees in there, I get 60 degrees and 45. Well, those are values that I can actually do. Tangent of 60, we know those are the big reference angles. Those are √3s. Sine of 45, square root of 2 over 2. So I can take this and I can multiply by the reciprocal, which gives me 2 √3 over √2, and then rationalize, and then I end up with √6. So a little bit weird, but don't forget to plug in the a value, all right? All right, jumping to this graph. I'm going to leave the graph up on the screen as I roll through these. You have the key up on Schoology. There's a chance you do maybe as well, or you've already completed these, but I'm just going to call out the numbers and go A, B, C, D, and then, so I'm going to point to the graph what I'm doing. So the first one, 36, A, B, C, D. The limit to infinity. Well, as I head to infinity, I've got this dotted line in there suggesting it's a horizontal asymptote. So I would argue that the limit here is approaching a value of 1. All right? And then the limit as you approach -9. Well, at -9, it looks like from the left I'm going to -2. From the right I'm going to +2, so that doesn't exist. What's the value at -9? The value at -9 is that point. So that's a -2. And then D is just a bad question. I can't ask you, and I did that on purpose. But people say, why is it a bad question? What's f of -infinity? It should be equal to 1. Well, I can't evaluate a function unless it's a value. If you start thinking, oh, f to -infinity, that's what a limit is. That's what 36a was asking. So that's just a bad question right there. Smiley face if you're looking at the key. All right, 37. 37 said, what's the limit as I approach -4 from the left? Well, -4 is right here. From the left, it looks like I'm approaching 4. From the right, it looks like I'm approaching 4. So the limit exists at 4, okay? But D says, what's the value of f at -4? Well, the value is 1 because there's a dot right there. All right, so we would definitely say the graph is not continuous there and not continuous at -9 because the limits and the values, here the limit doesn't even exist, but here, even though the limit exists, the value for the function at -4 is not the same as the limits result. All right, 38's asking you about 0. 0 from the left is down there at -3. 0 from the right is up there at +1. That's A and B. And then so C, the limit does not exist because I'm not approaching the same thing. But the value does. F of 0 is 1. But this would definitely not be continuous, right? I mean, you can see it and see that it's not continuing. It's hopping up this jump right here. But you can see the rules have been broken, the rules for continuity. 39 is asking you about here at 3. 39a says the limit from the left looks like I'm going to -infinity. The limit from the right looks like I'm going to +infinity. So definitely the limit does not exist on C. And there's not a value there either, so the value does not exist. But don't ever look at C and D, guys. Don't look at this and go, oh, right here, the limit and the value were the same, so it must be continuous. Don't do that. Remember, the rule is the limit has to exist. This does not exist. It says the value has to exist. Does not exist. It's not just so much that they match, okay? Right? That has to exist and they have to actually be equal. And then 40 talks about the limits at 7. Limit from the left, -infinity. Limit from the right, -infinity. The actual limit, therefore, is -infinity. Now, granted, that still means it doesn't exist, but the limit, we write -infinity. And then, of course, there's no value there. So f of 7 is D and E. And, of course, it's not continuous at 7. And then the last one's just talking about some couple of random things. First one says, what's the limit to infinity? Well, it looks like it continues to rise. So 41a, I would say infinity. The limit as x approaches 9. Well, that's just that value there. So whatever, it kind of looks like 1 or 1.1. I don't care. Whatever you want to enter. If it was a multiple choice question, you would probably have like 1 or 9 or something weird like that. I don't know. And then what's f of 9? Well, f of 9 has a value there too. That's also whatever you put for B will be for C. And then D, again, bad question. I can't take a limit to infinity. I mean, I can't take a value, f of an infinity, because infinity is not a value. All right. The thinking on that, if you're thinking it's the answer should be infinity, is what you did for 41a. That's a limit. All right. So hopefully that kind of makes sense. Most people do really well on that part on a test. 42, find the limits algebraically. So again, I see a 3. Don't go using power rules and say that this is 5. Don't do that. That's limits to infinity. So plug a 3 in. Take your time. 45 plus 1 is 46. Minus 6 is 40. 9 and 1 is 10. Simplifies to 4. Great. Plug a -2 in. And by the way, don't go and factor stuff every single time you see a polynomial or a trinomial. Don't do that. Remember, we only factor if I get 0 over 0. Like, even if this did factor, why would I try if I don't know I need to? I don't need to. Like, this one factors greatly. But if the limit is going to 5, I don't need to do that because 5s don't give me... I mean, you can if it factors and you cancel. It's not going to hurt your answer, but it's a waste of your time. So because I got 4 plus 6 is 10, minus 10 is 0, over 0. That's why I factored, canceled, and then plugged the -2 back into this. All right, and then over here, I'm plugging a 5 in. 25 minus 15 is 10. 10 plus 10 is 20. And then 25 minus 25 is 0. That's a VA, right? That means vertical asymptote. The bottom is not squared. Now, if you look at that and go, but the t is squared. Guys, isn't it pretty clear that if I plug a t like 4 in there, that I'm going to have a negative, or 4.9? But if I plug a number like 5.1, I'm going to have a positive, right? This is not the same as having the entire bottom squared, or the entire bottom absolute value. So because we know it's a VA and the whole bottom is not squared, I got to go DNE. All right, 45, a little bit more stuff with continuity. It's basically walking you through the whole continuity thing, although then I never really asked you continuity, but I will. 45A right here, let's take a look at this piecewise function. Okay, says, is the limit of this function exist as you approach -2 from the left? Well, there's -2 from the left and I get a 5. -2 from the right, -2 from the right, I get 3 minus a -2, which is also 5. So because the limit left and right are the same, yes, the limit exists, right? And it is 5. And then the value, f of -2, also exists because there's an equal. That's also 5. So this, because the limit exists and the value exists and they're equal, I know it's continuous at -2. I didn't ask that, but I would on a test. But that's how you check it. So I know that this parabola and this negatively sloped line do connect, right? Somewhere, and I don't even have to graph to know that because I checked my rules. And then the value of f of -8, f of -8 I guess would fall on that top line. So 64 plus 1 is 65. And then on part B, it says, let's look at as you approach 1 from the left. 1 from the left would be 2. 1 from the right would be the bottom equation. That would be also 2. So the limit does exist, and it's 2. And then the value, I didn't ask you for the value. Yeah, I did right there. The value at 1 is 4. So because the value exists and the limit exists, but they're not equal, these do not connect. All right? So these two graphs would not connect, and therefore it would not be continuous at x equal 1. And then I threw in f of 3. F of 3 would fall in that interval, so I plug it in there, and 30 minus 8 is 22. All right, cruising along, 49 through 52 on this line. 49, I've got a limit to infinity. That's all about my power rules, bigger power on the top. I don't even have to look at that stuff. It's all about, does this go to infinity or negative infinity? Well, if I plug a positive number there and there, that's positive over positive, so it must be positive infinity. Here, again, I'm going to positive or negative infinity. Power rules are in play. Bigger on the top, I don't even have to look at this. But if I plug a negative in there, I get a positive over negative. That's a negative infinity. Here, again, infinity rules in play. I mean, I'm going to infinity, so the power rules in play. Bigger power on the bottom, always 0. Bigger power on the bottom, always 0. I don't have to check anything. The only time I have to check for the sign is when when I have a bigger power on the top. 53 and 54, I'm going to 2. Don't look at power rules. I'm going to 2, plug a 2 in. Look, I get 48 over 9, done. But if I'm going to infinity on that same problem, then the power rules come into play. So bigger power on the top, nothing else matters but the highest power. So negative there, I get a plus over minus, it must be negative infinity. And bigger power on the top, again, don't get sucked in and go, oh, it's bigger power on the top, it must be positive infinity. No, I'm going to 0, plug a 0 in, and I get 0 over 1, which is 0. Answers make me happy. Okay, 56, I'm going to -1, plug a -1 in there, I get 3, plug a -1 in there, I get 0. What does that mean? There's a VA. If there's a VA, I know that this graph is not going to exist unless the entire denominator is squared or absolute valued, and it's not, so DNE. Now again, if I'm coming in from the left, -1 from the left or -1 from the right, that's when I'd have to come in here and say, okay, let me plug in like a -1.1 or a -0.9 and see what the sign is on each side. But if I'm just coming to -1 from both sides, done. All right, 57. All right, probably zoom in on that a little bit, help you to see. 57 right here, I'm plugging a 3 in, I get 0 over 0, so I factor the denominator, cancel. I'm left with 1 over x plus 3, redo the limit. 58, I'm going to infinity. Looks just like 57, but I snuck in infinity. Go to your power rules, bigger power on the bottom, must be 0. Right? These are all my horizontal asymptote rules. Okay? And then fit from pre-cal. So right here, I'm going to 0. I get 1 over -1 is -1. Great. On number 60, I plug a -1 in. I get 0 over a 1 minus 1. It was also a 0. I factor the bottom, cancel the factors, redo the limit, and get a -1/2. All right, so hopefully we're rolling along. Almost finished. 61. I've got this right here. I'm going to infinity. I look at the highest power. Don't get sucked in and go -3/2. These are your two highest powers right here, right? And it's bigger on the bottom, so I know I'm going to 0. Make sure that you're careful to look at the highest powers on the top and the bottom, and not just the first ones. These are not always written in order, and AP likes to do that. Next year, you'll see that. Here, highest power on the top, so all the other non-highest powers don't matter, so I'm focusing in on these two. A negative infinity there becomes a positive times a -3, so negative on the top. A negative infinity on the bottom becomes a negative times a 2, which is a negative on the bottom. Two negatives make a positive infinity. And then these problems, they're a little tricky. We've talked about them before. I'm going to slow down and walk you through it again. Remember, I'm going to infinity, and I'm like, crap, I don't know what this thing looks like. So I'm going to think a little bit. Could I simplify the square root of a 16x squared? Well, I don't get 4x to get absolute value of 4x. Now, I don't get exactly absolute value of 4x because of the 5. It's absolute value of 4x, something that I don't really know. And listen, there's another way to do this, and we've talked about that, dividing the bottom by the square root of x squared, square root of x squared, the top by -x, because I'm going left. But we've talked about this way more. So now that I've gone from here to here, let's think about it. Remember what absolute value looks like. Sometimes it's positive, it's going that way. Sometimes it's negative. So sometimes I leave it alone. Sometimes I change it and negate the bottom. Well, I'm going to the left. That's the negative part of the absolute value. So I'm going to take this and negate it to get rid of the absolute value because I'm going left. If I was going right, I would use positive 4x because I'm using the right side. And once I get this from that to that to that, now I have the same power. Infinity, use my coefficients. So it's a nice logical way to go through it. Now 64 is much easier because 64, you have a cube root. Cube roots don't have absolute values. So the second I cube root that, I get to 2x. There's no absolute value to deal with. At this point, it doesn't really matter which way I'm going because if the powers match, 3/2. But here, you had to consider the fact that I was going left and use a -4x. Got to do it. And that's arguably the trickiest question on your test. And yours, in the day of Corona, will be open notes. Okay, I'm shrinking this back down so you can see this graph all at once. All right, so 65, A and B, we're looking at this graph. What's the limit as I go to infinity? Well, if I didn't have the dotted line in there, I mean, you could guess -1, you might guess 0. So I'll probably put a dotted line or make it really clear. AP is really clear about that stuff and typically doesn't ask questions about graphical limits. But anyway, you can see that my limit is approaching a -1. It's flattening out at -1. And again, bad question for f of infinity. I probably need to get rid of those, but anyway, 66a, I'm going to -3. The limit is right there at about 2, and then the value is down here at about -2. So definitely not continuous there because the limit and the value, although they exist, aren't equal. But it's clear to see that here. Right here on 67, 67 is asking you about 2. Well, that's totally continuous. So the limit and the value, you know, are going to exist and they're going to be the same because it's continuous there. And sure enough, the limit is equal to -3. The value is equal to -3, and they match. And then finally, at 7, the limit does not exist because I'm approaching -1 from the left and +2 from the right. So that's a DNE right there. But the value does exist here at 2 or about 2. All right, and if this is you know, like I said, it'd be a multiple choice test, most likely. So pick the one that's the closest. Even if it is, if I gave you something like this and it was, you're like, man, I think it's 1.9. Well, it's closer to 2 than it is to 1. So just go with that. All right. And then finally, I got one more graph to look through, walk you through. 69 says, what's the limit as I go to -infinity? Well, as I head off to the left, it looks like it's oscillating between a 0 and maybe a 2. Well, what did we say? Anytime you oscillate between two fixed points, the limit doesn't exist because the limit is the y value. So there is no y value for that. But on the right, it looks like I'm not oscillating. I'm just flattened out there at 1. So the limit to infinity down below at 73 should be equal to 1. Okay, I'll just move across the right. So number 70, the limit of this function at -5. Well, there's no limit because there's nothing from the left, even though from the right, it looks like it's approaching a value of 2. So I'd have to say DNE. 71, the limit as I approach x equal 1. Well, right here at 1, it looks like both sides are diving down to -infinity. So that's the limit there. And at 72, the limit as x approaches 4, they're going up, down, and up from the left and the right. So I got to go with D and E. We've already talked about 73 being 1, because as I head to the right, I'm flattened out on the graph there at 1. And then the limit as I approach -3, I'm right here. As I approach -3, both sides are going up to infinity. So I say infinity, even though we know that the limit doesn't exist at 70 on 71 and 74, we say -infinity and +infinity because it's a little bit more, gives us more information. 75, what's the limit at 0? Oh, well, that's continuous there. So the limit's going to exist, the value's going to exist, of course. The limit's -2, same as the value. And then at x equals 12, well, I can't even see 12, right? 4, 5, 6, 7, that's 8. It only goes out to 9, but we can assume right there, if I'm flattened out at 1, I'm going to continue to flatten out. It's my best assumption, so I'd have to go with 1. All right? All right, guys, hopefully you're in good shape at this point. I'm going to give you a couple more days of this stuff. I'm hoping that you're doing the actual problems, and then once you do the problems, you check the video for whatever you need. All right? See you tomorrow.